Let's graph some rational functions. I'm going to assume that you already know how to find the equations of the asymptotes of a rational function. If you don't, I would suggest going back to watch some videos that covers that information. Let's move forward and we'll use those asymptotes and of course the x and y intercepts to help us get a good graph. So let's jump in. I always look for the vertical asymptotes first. Notice with this equation, we have f of x equals 2x plus 1 over x minus 3. We're looking at the denominator, and we see that x minus 3 would equal 0 when x equals 3. So we have a vertical asymptote at x equals 3. Horizontal asymptote. The degree of the numerator is equal to the degree of the denominator, so we look at the coefficients of those terms of highest degree. So we have a 2 over a 1, so we know we have a horizontal asymptote at y equals 2 over 1, or just 2. Now an oblique asymptote or slant asymptote exists when the degree of the numerator is 1 greater than the degree of the denominator. We don't have that happening, so I'll just say none. Let's move to the intercepts. The x-intercepts we find by setting y equal to 0. In this case, that's f of x. So we have 0 equals 2x plus 1 over x minus 3. We multiply both sides by x minus 3, and we have 0 equals 2x plus 1. So we can solve that linear equation, and we get x equals negative 1/2. I'm going to write it as an ordered pair to remind you this is a point, as opposed to the line up here where we have x equals 3, where this is the equation of a line. Now let's move on to y-intercepts. To find the y-intercept, you make x equal to 0, so that means we have y equals 2 times 0 plus 1 over 0 minus 3, and we have a y-intercept at negative 1/3. So again, as an ordered pair, it's 0, negative 1/3. Let's put all of that onto a graph and see what it looks like. I'm going to put in my vertical asymptote at 3. Let's make that be right here. Oh, pretend that looks like a vertical line. Here's 1, here's 2. I have a horizontal asymptote at y equals 2. Let me draw that in as well. And of course, label those because those are important. And these asymptotes are our graphing guides because we know the graph will approach the asymptotes. So let's see, what else do we have? Our x-intercept is at x equals negative 1/2. That puts it at about right here. And we have a y-intercept at negative 1/3, and that puts it about right here. And I'm going to label those. Those are a little hard to read. This is at negative 1/2, and this right here is at negative 1/3. When we're graphing rational functions, the vertical lines chop up the plane into different parts. So we have to figure out what the graph looks like to the left of 3 and to the right of 3. Let's start to the left because we already have a couple of points. Since the graph will touch those points, I know I have a little piece of the graph this way. And then we know that the asymptotes are graphing guides, so I know the graph must continue up this way toward this asymptote. Now let's see, to the right, between 0 and 3, there are a couple of things you need to consider. Does the graph do this? Because graphs can do that. Or does it continue going down and head toward the asymptote this way? Which of those is correct? And based on the fact that we have no more x-intercepts, we know it can't be this. It must be heading toward negative infinity as it's going toward that asymptote at x equals 3. So let me erase. So now I have it looking correct to the left of 3. Now let's look to the right of 3. Again, keep in mind that your asymptotes are your graphing guides. So the graph must look one of two ways. Is it going to look like this and approach the asymptotes up here? Or is it going to look like this and approach the asymptotes down here? And again, the absence of an x-intercept lets us know that this cannot be it. Because if we had a graph down here, notice there would be another x-intercept. So again, let me do some erasing. And it looks like we have the graph finished. There is one more detail, though, that I want to address. How do we know that the graph doesn't cross the horizontal asymptote? A rational function cannot cross or touch a vertical asymptote because that's where the function is undefined. But they can and do sometimes cross the horizontal asymptote. So for example, how do we know the graph doesn't actually come down this way, cross the asymptote, and approach from below? Well, here's how we're going to figure out whether it does or does not. If it were to cross, notice there would be a point on the curve where the y value was equal to 2 because it's on the asymptote, that horizontal asymptote. So let's ask the question, does the graph cross y equals 2? If it were to cross, there should be a point on the function where the y value were equal to 2. So let's let it equal 2 and we'll solve the equation. So I'll multiply both sides by x minus 3 and solve. So we have 2x minus 6 equals 2x plus 1. Subtract 2x from both sides, and we have negative 6 equals 1. And there is no solution for that. That means that there is no place on the graph where the y value is 2, and hence it does not cross the line y equals 2. So again, we can erase. And we have our graph complete. Let's see how it compares to the graph when the computer does it. Here it is. And you see it looks just about the same. Let's move on. This one will be f of x equals negative 3 over x squared minus 4x minus 12. So let's roll through the information that we need to get started. So vertical asymptotes, we know we need to look at the denominator. So let's factor the denominator. I'm just going to rewrite the function right here with the denominator factored. So we would have x minus 6 times x plus 2. Neither of those is a factor in the numerator. So we know we have a vertical asymptote at x equals 6 and another one at x equals negative 2. Moving on to horizontal asymptotes. We see that the degree of the numerator is smaller than the degree of the denominator, so I have a horizontal asymptote at y equals 0. And if I have a horizontal asymptote, I do not have an oblique asymptote. Those cannot happen at the same time, so there's none. Let's move on to x-intercepts. To find those, we set y equal to 0 and solve. And we can use either version of that function. I'm going to multiply both sides by x squared minus 4x minus 12, and I get 0 equals negative 3, and that equation has no solution, so there are no x-intercepts. Moving on to y-intercepts, you set x equal to 0, and we would have y equal to negative 3 over 0 squared minus 4 times 0 minus 12. That's negative 3 over negative 12, or 1/4. So let's write that as an ordered pair, 0, 1/4. Let's draw our grid and see what we can come up with. Our intercepts, or excuse me, let's start with the asymptotes. They're at x equals 6 and x equals -2. So let's see. I'll put right here will be my vertical asymptote at 6, and then at -2 will be right here. It's hard to see a dashed line on top of a solid line, but let me put it in anyway just to remind you that we have a horizontal asymptote right here at y equals 0. That's our x-axis. Let's go on. Let's put our intercepts on. We don't have an x-intercept, and that's actually helpful because we know that the graph will neither cross nor touch that x-axis. But we do have a y-intercept of 1/4, so let's put that on. Right here at 1/4. And here we go. We're going to graph this function. The vertical asymptotes, again, divide the plane up into 3 parts. So we'll find the graph to the right of 6, over here, in between -2 and 6, and to the left of -2. Let's start in between -2 and 6 because we have 1 point. Because we know the graph cannot cross the x-axis because we had no x-intercepts, we know the graph must live above the x-axis and it must approach the asymptotes. So I know that the graph must look something like this. And I don't know how far down it goes. I don't even know if it's symmetric, but I'll make it look like this. And that's a rough sketch. To have more detail, we'd need to plot some points or use some calculus if we were going to do this by hand. Let's move to the right of 6. I need to know whether the graph is above the x-axis or below the x-axis. And because it must approach those asymptotes, I know it must look like this or it must look like this. Which one is it? Well, here's where interval testing can come into play. Remember our interval testing. Let me come over here. Our critical values for this function are at 6 and to -2. And if you pick a number to the right of 6 and throw it into the original function, you'll notice you'll have a negative over a positive times a positive. You could just put a number like 8 in there and you'd have a negative over a positive times a positive. And that is negative. Similarly, you pick a number between -2 and 6 and you'll get a positive value. Oh, and notice how it confirms what we knew, that the graph is up here. And to the left of -2, we can substitute in a value like -10, and you'll find that you have a negative over a negative times a negative, which is again negative. So now let's use that information and come back to our graph. To the right of 6, what do we see? That the values of the function are negative. That means they are below the x-axis. They're down here. It cannot be this. So let me do some erasing. Now we're looking to the left of -2. And again, I see that the function has negative values there. So that means to the left of -2, the graph must be down here. So if I draw my curve and again use those asymptotes as your graphing guides, I know it's going this way and down this way, and we have the graph complete. Here's our next one. Let's roll through our asymptotes and intercepts, starting with the vertical asymptotes. In order to see those, I like to look at the function with the denominator factored. So we have x plus 1 over x plus 2 times x minus 2, because we have the difference of 2 squares. So my vertical asymptotes come from that denominator. Notice neither of those are a factor of the numerator, so we have vertical asymptotes at x equals -2 and x equals +2. When we consider the horizontal asymptote, we know that the degree of the numerator is smaller than the degree of the denominator, so we have a horizontal asymptote at y equals 0. Since we have a horizontal asymptote, there is no oblique asymptote, and of course, the oblique asymptote occurs when the degree of the numerator is 1 bigger than the degree of the denominator. So we have none there. Let's move on to the x-intercepts. We set y, or in this case g of x, equal to 0. So we have 0 equals x plus 1 over x squared minus 4. Multiply both sides by x squared minus 4, and we have 0 equals x plus 1, or x equals negative 1. And let's emphasize that this is a point, negative 1, 0. And we move on to the y-intercepts, and the y-intercepts we get by making x equal to 0. So we have y equals 0 plus 1 over 0 squared minus 4, and we have y equals negative 1/4. So 0, negative 1/4 is our y-intercept. So let's write all of that on our grid. Our vertical asymptotes are at 2. Ooh, would have been nice if that x-axis had been horizontal. Doesn't quite look like it. There's negative 2. My horizontal asymptote is on the x-axis. My x-intercept is at negative 1, and this is a nice reminder that the graph can cross or touch a horizontal asymptote. It cannot cross or touch a vertical asymptote with these rational functions, but it can cross or touch a horizontal asymptote, and it's going to either cross or touch there at negative 1. And let's see, what else do we have? We have a y-intercept of negative 1/4. Now, we could draw some of the graph based on this information, but I talked about our interval testing on the previous problem. I don't use it every time, but I want to show you again in case you want to use it. So right here, our critical values from our function are at negative 1, at negative 2, and positive 2. Pick a number to the right of 2 and substitute it in, and you'll find you have a positive value. And then it will go negative, and then positive, and then negative, right? Just by choosing a number in that interval, substituting it into your function. So now let's see what the graph would look like. To the right of 2, the graph must be positive. It lives above the x-axis, and of course it must approach the asymptotes. So that means our graph will look like this. In between negative 2 and 2, I have that it is positive between negative 2 and negative 1. That means between negative 2 and negative 1 is right here. It's above the x-axis. So I'm going to draw that in. It means it's going above, and of course it has to approach that asymptote. And to the right, it goes negative. And of course, even without this interval testing, we would know that because there is a y-intercept right here. So let's draw it. Comes down and crosses. I don't know exactly where it curves, but ultimately it has to curve down toward that asymptote. And to the left of negative 2, I see that it is negative. So that means the graph lives below the x-axis there. And still we have to have our graph approach the asymptotes, so it would look something like this. And we have our graph complete. This will be our last example. Let's find the asymptotes and intercepts to begin. And again, to start, I'm going to factor that denominator. So I have x plus 2 in the numerator, and let's see. We have an x and an x. 5 breaks up into 5 and 1, and we're going to put a minus on each. So our vertical asymptotes come from that denominator. And again, notice that they don't have the same factor in the numerator as the denominator. So I am comfortable saying that we have vertical asymptotes at x equals 5 and at x equals 1. We're moving on to horizontal asymptotes. Notice the degree of the numerator is smaller than the degree of the denominator, so we have a horizontal asymptote at y equals 0. And of course, because we have that horizontal asymptote, we do not have an oblique. Let's move on to x-intercepts. We set y equal to 0 and solve the equation. We multiply both sides by that denominator, and we have 0 equals x plus 2. Subtract 2, and we find that we have an x-intercept at -2, 0. For our y-intercept, we'll make x 0, so we have y equals 0 plus 2 over 0 squared minus 6 times 0 plus 5. That means we have a y-intercept at 2/5. Let me write that as 0 2/5 to make it very distinct from our linear equations that we have above that represent our asymptotes. So let's get all of this information on our graph. Let's see, vertical asymptotes at 5 and at 1. We'll put 5 right here and 1 right here. We have a horizontal asymptote at y equals 0. That means the x-axis is a horizontal asymptote. Our x-intercept is at -2. And we have a y-intercept at 2/5. So here we go. Let's start to the left of 1 because we can see how the graph has to look. From -2 to the right, it has to come up toward this y-intercept. It cannot turn down and head toward the vertical asymptote going down because then it would have to cross the x-axis. So it must continue going up this direction toward our asymptote. Now at -2, one of two things can happen. It can just touch, but it would still have to come back down and approach the asymptote since we have that horizontal asymptote, or it can cross and come back up and approach the horizontal asymptote. Notice there are no more x-intercepts, so it will not cross the x-axis again. So which one is it? And there are a couple of ways to tell. You can essentially interval test, substitute in a number to the left of -2 and see if it's positive or negative. Or we can use the fact that the exponent on this x plus 2 is to the first power. Just like we saw when we were graphing polynomial functions, if this factor is raised to an odd power, it will cross. So we know for this part of the graph, it's going to cross there. So let me erase this part up here. So we have our graph. It crosses, goes down, and make sure it looks like it comes back up. Between 1 and 5, we need to know whether it's above the x-axis or below. It must be either up here. And by the way, it looks symmetric when I drew it, but we have no reason to believe that it is or is not. I mean, it could be sort of skewed this way. I mean, it could look, and they do sometimes look like this. We just don't know. We're not plotting points. We're not going to do anything that will tell us that. We're just getting a rough sketch. But to determine whether it's above or below, we can pick any number to the in between 1 and 5, like 3. And pop it in, essentially do our interval testing. But right here, put a 3 in. We'd have a positive, a negative, and a positive. The result is negative. And so I'm going to erase this part up here. And I have it skewed that way. It may look like that. It may be more symmetric. We just don't know. To the right of 5, again, we need to know if it's above or below the x-axis. We know it can't cross. So let's pick a number to the right of 5, like 6. Pop it in, and you'll find that you would have if you put a 6 in, you'd have a positive value here, and a positive value here. And so our graph would look something like this. since we know the result would be positive and hence above the x-axis. And there's our graph for this rational function. I hope you'll watch the next video and look at some more advanced rational functions.